Hello everyone, I'm Yuandong, a platform researcher of the Unisound AI Labs. I'm glad to participate in the second data Orchestration conference. Today I will share some use cases about speeding up in Atlas deep learning platform with Alluxio and Fluid. Let's go through it. Firstly, I will give a short introduction about the Unisound and the AI platform. Then I'd like to talk about the challenges and compromise solutions for our platform in daily use. Next, I would like to share 3 application scenarios in our daily use, including noise reduction, image classification, optical character recognition. And I will list the results of comparable experiments and analyze why Alluxio is beneficial to us. And then I will list a couple of contributions of Fluid. Finally, I would like to make a conclusion and list the future work. Unisound is a world-leading artificial intelligence products and solution company. We provide customers with full-stack integrated solutions, including algorithms, software, and hardware products. Based on full-stack AI technology through cloud, gauge, and chip, Unisound created an ecological closure from AI technology innovation to infrastructure applications. Products and solutions are widely used in our home plans, medical, financing, education, transportation, automobiles, real estate, and so on. Our company has more than 20,000 partners, covering more than 200 million users, covering 517 mini cloud platform codes every day, and covering over 250 mini devices. Atlas AI platform with sufficient computing power and machine learning algorithm to quickly expand our company in speech and semantic understanding computer version technology. In order to support our algorithm research in AI labs, a uniform deep learning platform to support the various applications is needed. As a worst company, the most of business comes from speech processing, but we also actively expanding other business such as computer version and natural language processing. So there are a variety of training jobs running on the platform, such as speech processing, image processing, semantic processing, recommended system, data mining, and text analysis. In computing lab, we need to support data processing, feature extraction, and statistic analysis job. Differential many different environments and frameworks like TensorFlow, PyTorch, or Aminet. So we choose the container as the runtime of all jobs. And we choose the Kubernetes as the container scaling and the measurement engine for Atlas AI platform since 2016. In order to use the platform more simply, we integrated and developed some components such as user management, image register, and model register. Users can manage their own experiments, image and models through a uniform account management system. For improving the efficiency of the platform, we have developed the new distribution job scheduler and resource management components. Of course, logging and monitoring are also essential. The last, the infrastructure. Our platform has different, different computer cluster and storage cluster. High-speed interconnection between them through a 100 gigabit infinite band high-performance network. Let's go next slide. I would like to introduce the storage of our platform, Lustre. Lustre is widely used in APC field. The distributed field storage system can provide a continuous petabit scale spaces. It provided data verification and replication to ensure data security. Considering the cost and workload, we have multi-cluster cluster with different networks, such as InfiniBand and Ethernet. We have developed a series of tools to simplify the installation of cluster and support online expansion and version update. As this image shows one of our cluster cluster. When using cluster theory storm, we will encounter some challenges. Those challenges will affect the normal stability and the essentials of the Intel platform. The challenge is the I/O pressure of storage. Some of tasks read and write the same storage at the same time due to different application and different data. It is impossible to configure cluster optimally and uniformly. There are many images and audios are smaller than 1 megabit in computer version and the speed progressing application. However, cluster architecture is not very good for small field I/O, especially lots of small fields. Cluster needs to interact with metadata service before reading and writing fields to obtain relevant attributes and after allocation information. Compared with the local field system, addition transmission network and metadata access overhead is added, which is quite large for small field I/O. For large number of frequency, small fields read and write. The cache function of last client will fail and the hit rate will be greatly reduced. If the field is smaller than the physical page size, will generate additional network traffic. And the next change is I/O permutation for different tasks in same node. And the last change is data duplication because user had own storage location with self-information. The impacts changes is obvious. Some fields and I/O pressure will cause low quality of service or platform training, and the I/O permission will waste computer resources and duplicate data may be in different user spaces, which will greatly waste the storage capability. We have taken some measures to ensure quality of service or platform. We manually limit the client rate for some nodes with low computing capability, such as two commands below. The two command means that the client rate limit TBF need policy. TBF means token bullet bucket filter, and the limit rate is 320 megabit per second when RPC size is 4 megabit. And we recommend to the user pack some field or convert the to large field format. We're also doing related work at the scheduling layer. The scheduler will priority scheduling task to idle node. Last, we recommend the user of the same group check the same date in their location. But effectiveness of the solution is limited. In order to solve the problems, we designed a new platform architecture that uses a cache layer between computer layer and storage layer. And we choose Alluxio as cache engine and the Fluid as engine management. Fluid dataset object declares the amount passed in cluster, and the Fluid runtime controller will create components of Alluxio engine, including master, worker, fields, job master, and job worker. We use Linux default access controller for use field permission. Permission control can be automatically injected into Alluxio components through Fluid runtime. And the dataset can prewarm the amount pass. It will greatly reduce the time to read data from cluster into cache. We believe cache is all we need, but why we choose Alluxio engine? I think there are three benefits. The first is that the performance of Alluxio is very good in the set we tested. And the second is that Alluxio's framework determines that it is easy to expand, even to thousands of nodes. Third, Alluxio is open source. It has a strong community support. Why we chose Fluid? As I mentioned before, our platform including speech, computer version, and natural languages processing. It will have different types of this set. We have made a statistic on all the data, roughly divided into the following three categories: massive small fields, medium-sized fields, and large-sized field. For example, many images and space segments less than 1 megabit. One task will create massive small field. Some classification task will treat each class as a field from 1 megabit to 100 megabit. And for some tasks, it will use MDB to processing the data as a large field. When we start using Alluxio engine, we will meet four problems. One is how we manage different user data set. And the second, how to speed up different types of data set. The third, how to outscale Alluxio engine. Last is how to scale circular job with catch located. Thanks to the in-depth cooperation with Fluid and Alluxio, we optimally those three types and use the Fluid scale for outscale, ratio, expansion. In next few slides, I will like to share some tests in different deep learning scenarios. We tested three types: massive small field of noise reduction application, medium-sized field of image classification application, and large-sized field of optical character recognition application. We will make comparative experiments between reading directly from raster and reading from Alluxio catch. For massive small field, noise reduction application use nearly 183 gigabit for 500 sound fields, and we set catch in memory were Alluxio configuration. There are three experiments. One, raw waves fields from raster. Second, train data from no pre-warm Alluxio. Noise data from raster. And the third, outdate from pre-warm Alluxio. In this slide, we can see reading from pre-warm Alluxio catch is 10 times faster than reading from raster. The speed of reading from Alluxio and raster together have improved, but not much. And we can see reading from pre-warm Alluxio catch reduced bandwidth usage from 230 megabit per second to 0 and increased GPU usage efficiency by 10%. So our bottleneck will limit GPU compute capability. For medium-sized image classification application will nearly 138 gigabit of one sound TF record field. There are two experiments, exclusive job and permutation job. The permutation job means more than one task running on the same node at the same time. And we can see reading from pre-warm Alluxio catch is 2.5 times faster than reading from raster. For large field, optical character recognition application will use 100 to 25 gigabit of 1 MDB field. There are three experiments reading MDB from raster, reading no pre-warm MDB from Alluxio, reading pre-warm MDB from Alluxio. In this slide, we can see reading from pre-warm Alluxio catch is 30 times faster than reading from raster in early iteration. When MDB field is all in memory, the speed is almost the same. And we can see Alluxio reading MDB from raster is faster, and pre-warm can be done when node without tasks. Reading from pre-warm Alluxio catch reduce bandwidth usage from 15.6 megabits per second to 0, and increased GPU usage efficiency by 31.5% compared to directly reading from raster. In experiments, we will find 3 points. Fluid with Alluxio engine not only can greatly speed up different types of design training, but also increase the GPU usage of tasks. And the Fluid with Alluxio engine will greatly reduce the pressure on large distributed field system. We are also actively collaborating with the community and continuing to contribute to the community. Let's make a summary. So why the new architecture can speed up? I think the first reason is high performance of Alluxio architecture. The second is we and the fluid custom and optimize Alluxio parameter with different scenarios and dataset. And the last reason I think is fitting. Data is always immutable in deep learning life cycle, and deep learning needs deterministic job, so it fits Alluxio. Locally based scaling is needed for Lustre, and capture different tasks is needed, so it fits Fluid. And in the future, I would like to try more scenarios for Fluid with Alluxio engine and sharing best practice. We will also make a continuous contribution for community. Thank you very much for listening.